to talk about a new discovery made by Andrew Vanderburg, professor at University of Wisconsin in Madison. Hi, Andrew. How are you?
I'm doing great. How are you?
I'm good. Are you in your office right now?
I'm in my home office.
Your home office. Good. So Andrew is the lead author of a paper that was published in Nature last week about the discovery of a planet in orbit around a white dwarf. So this paper has been published in Nature, as I mentioned, and has been basically reported in various newspapers around the world. I saw that you have some very great title on the CNN.com, on space.com, talking about a planet around the body of the corpse of a star. So before we enter in the detail of your discovery, could you please tell us what is a white dwarf?
Yeah. So stars like the sun burn hydrogen fuel in their core in nuclear reactions. And that's what produces the light that we see on Earth and what keeps us warm and what keeps us energized. But that hydrogen won't last forever. And eventually stars like the sun will run out and they will no longer be able to continue fusing hydrogen into helium in their cores. When that happens, they'll expand briefly, they'll get very large, and then eventually they'll lose their outer layers. And what will be left is a small, hot core that's no longer producing its own energy. It's glowing from the leftover energy of the star. And that's a white dwarf. It's basically what's left of a star like the sun after it runs out of nuclear fuel and dies and ends up remaining there for much longer than the star was actually alive, for essentially the rest of the universe.
Yeah, I used to say that the white dwarf is kind of the skeleton of the star, basically, what remains after the star, which sun-like stars basically disappear. Great. So what happened? Why did you publish something in Nature? What is this big discovery? Can you tell us a bit what exactly your program has been about and what was the discovery?
Yeah, so one of the questions that we try to answer is what happens to the planets that orbit a star after that star runs out of fuel and dies? We're pretty sure that the inner planets are not going to be very safe. In fact, during the time when the star is expanding, they'll be engulfed by the star. So the inner parts of solar systems will be engulfed. But what happens to that outer part? It should survive the engulfment because it's far enough away to avoid that. But then what happens? Does it keep orbiting the way it was? Do they get lost into space? And in other cases, does it happen to be the case that those planets migrate and come back in close to the star? So that's what we were looking for. We were looking for, in particular, anything that came near the star after it died and came close enough to potentially be ripped apart. So in reality, we were looking for the debris of planets that were orbiting near white dwarfs. But what we found instead was a planet that appeared to be intact, that appeared to have survived the process of the star's demise and made it back in close to the star where maybe it could be warm. So yeah, go ahead.
Yeah, so how did you do this discovery? I'm assuming you use a telescope. We are talking about a faint star here, like magnitude 17 for people who are aware of. Then how we quantify the brightness. So it's a star which is 80 light years away from us, right? So what kind of instrument do you use to study or to search for exoplanets around those stars?
Yeah, so we use the Transient Exoplanet Survey satellite. This is NASA's newest planet hunting satellite. And what it does is it very carefully measures the brightness of stars all across the sky very quickly, very rapidly. So it takes observations of the stars every couple of minutes and it measures their brightness. And what it looks for is dips, dimming events in that brightness, which you could imagine could be caused by something orbiting that star and passing just between the star and our telescopes so that it casts its shadow on us and causes us to see a little bit less light from the star than we were before. And that's how we found this object. We saw that this white dwarf appeared to very briefly be dimming every day and a half or so when it was observed by TESS, which is the acronym for the Transient Exoplanet Survey Satellite.
All right. So before we dig into this in more details, please let us know where you're watching us. I saw that already some of you are watching us from UK, Montreal, Utah, Norway, Los Angeles, Louisville, Kentucky, Germany, Naples, Florida, Portugal, Hungary, Arizona, Italy, Montenegro, and Colville, Washington. I don't know all those places, but welcome and thank you for following us today on our SETI Live. So we are talking about a planet that survived around a white dwarf. So what's the name of this white dwarf and this planet?
This white dwarf is called WD 1856 plus 534.
Damn, you
And
managed to
it's a
remember
bit of a
this.
mouthful. So for short, we call it WD 1856.
Okay, so let's call it like that. So
Yep.
WD 1856 is the star, and WD 1856b is the new planet. So the planet is what? Earth, Jupiter, Neptune? What's the size typically?
So this planet is about the size of Jupiter, which means it's probably massive and probably has a large hydrogen-helium envelope on top of a smaller core on the inside.
And we talk about the white dwarf, the system. What's the size of a white dwarf typically?
White dwarfs are very small, and they're only a little bit larger than the Earth itself. So in the system, the star is much smaller than the planet that orbits it, although the star, of course, has much more mass, much more heft to keep that planet in orbit.
So that's why you have seen this attenuation, and it was kind of obvious attenuation compared to typically what we see when we observe an exoplanet, because the size of the exoplanet is significantly larger than the size of the star. Does the planet occult completely the system, or is that a partial occultation? What's the geometry here?
It's a partial occultation. So if it were a little bit closer aligned to our line of sight, it would block the entire star because the planet is large. But in this case, it's just aligned perfectly so that we see a little bit of light left during the middle of the occultation. So it blocks about 56% of the star's light. That's still about 50 times more than usually Jupiter-sized planets block around their stars.
So if you observe this planet, if you could see with naked eyes this star, we'll be able to see the dimming of this star every 1.5 days. And this dimming will last a few minutes, 18 minutes. That's what your paper reports.
8, yeah.
8 minutes, yeah. Okay, so that's the way you from this geometry, basically you infer the size of the planet. What else do we know about the planet? Do we know the mass? Do you know the composition? What other information can you get?
We don't really know too much about it yet, but we hope to be able to learn more in the future. So we know where it orbits. We know it orbits very close to the white dwarf. It's only about 4 times the radius of our own sun away from the white dwarf. We know that it's about the size of Jupiter, and we know that it can't be too massive. We know that it has to be less than about 14 times the mass of Jupiter, but it could be anything below that. It could be 1 Jupiter mass, it could be half a Jupiter mass, it could be 5 Jupiter masses. We just know it can't be much bigger than what we see.
So I love in your paper, the section where you describe the mass measurement, and in fact, the difficulty of measuring the mass for this planet, because we cannot use the classical technique, which is called radial velocity. I know it's a difficult thing to explain with your hands without figures, but can you tell us why it was not possible to estimate the mass of this planet more accurately?
Yeah, so usually when we see objects the size of Jupiter and we want to know if they're planets or something else, because it turns out that things the size of Jupiter could be just about anything. It could be a planet, it could be something a little bit larger than a planet called a brown dwarf or a failed star, or it could be a very small star. So all of those things are about the same size, it turns out. So if you want to figure out what your object that you care about is, usually the way you do it is by using the radial velocity method. And what this does is you measure very subtle changes to the color of the star as the star moves away from you and towards you. This is due to the Doppler effect, which you may be familiar with when you hear an ambulance going down the road. if you hear an ambulance coming towards you, the siren will be higher pitched. And then when it goes away from you, as it passes you, the siren will get lower pitched. The exact same thing happens with light and with color. But for this star, there was a problem. And that is what we actually measure when we look for these shifts are these very sharp bands of color that are either brighter or less bright than the light around it. These are the fingerprints of elements in that star. But this star was so cold and so dense and so old that it no longer has any of those fingerprints. So we were totally unable to use this technique, which is what we most often use to make these measurements.
So what did you do to infer the mass of the planet?
Yeah, so instead we had to use another method. And the idea here is that we wanted to measure how hot that planet could possibly be. We did this by observing with the Spitzer telescope, which is a telescope in space. It was recently decommissioned, but it observed an infrared light. So it was able to measure the amount of heat radiating away from relatively cool objects like planets. And what we found is that if our planet was particularly massive, it should have held on to some heat from when it was formed. We think that planets form hot and then they slowly lose that heat over the billions of years. But this planet has apparently lost enough of its heat that we couldn't see anything at all, which made us conclude that this planet must actually be a planet, because if it were more massive, if it had greater heft, then it would have held on to that heat for longer and we should have seen it.
Yeah, because young planets are very hot, but they cool down faster than brown dwarf, for instance.
Yeah.
Or stars, of course. So that's the way you kind of
boiling a pot of water. If you have a big pot, it takes way longer for that water to cool down than if you have just a little bit of hot water.
So you did not detect the planet directly by mid-infrared, we call emission. You detect the shadow of the planet from the star, but that gives you kind of an idea of the system. But you publish this in Nature because there is a surprise here. What is really the key part here, the key surprise? When you saw this, what was your reaction, for instance?
So the question is, how did that planet get to where it is today? Because I told you earlier that when a star dies, when it runs out of nuclear fuel, it puffs up really big and it engulfs all of the planets in the inner part of the solar system. So in our own solar system, our sun will eventually engulf Mercury and Venus, and it may engulf Earth as well, although Earth may just barely escape. But this planet is found way closer to its white dwarf star than Mercury orbits the sun. It's so close in that it definitely would have been engulfed if it had been there beforehand. So we think that this planet had to form and spend most of its lifetime far away from the star. And then it came in afterwards, after the star died and became a white dwarf. And that was the mystery. How could it do that? And how could it actually survive this process?
So that's basically, the planet might have been as far as Jupiter is from our stars. And when the system died, basically the planet started spiraling down somehow and stopped. And we still don't even know how, why, and it stopped. And we have no idea of the process that make it spiraling down toward its star. That's interesting, but I'm sure you have some ideas, right? You have some hypotheses.
So the first thing we thought was that perhaps this planet formed via a process called common envelope evolution. So the idea here is that the planet may have orbited a little bit further out, but it was still close enough to the star that it could have been engulfed while it was expanding in the red giant. And if an object does this, and it's big enough and it has enough heft, then it can actually survive that engulfment process. And it can blast off the outer layers of the star a little bit prematurely. And then it no longer is spiraling in. So we tried to calculate this and figure out if this was at all possible. And what we found is that it's really, really hard for it to work for something as lightweight as this planet appears to be. So even though this was kind of the first thing we thought about, and this is how we explain a lot of other things that orbit close to white dwarfs, it didn't really seem to work in our situation. So instead, what we think must have happened is that this planet orbited far away from the star, and it survived until the star lost its outer envelope. So when this happens, the gravity of the star, the white dwarf now, is weaker than it was before because it's lost this extra mass. It's lost all of its outer layers. And that means that its influence over anything orbiting far away is a little bit less strong. And when that happens, you can have planets that orbited far away start misbehaving because the influence of their star is not strong enough to keep them from pushing each other around. So what we suspect may have happened is that a couple of planets far out tugged on each other, pushed each other violently, and somehow shot this planet very close to its star. And when that happened, maybe that planet got close enough that it got a little bit stretched by the star's gravity. And that stretching ended up taking away some of the energy from its orbit and causing it to spiral inwards. So we have a lot of questions. We definitely have more questions than we have answers here, but we think some process like that could have caused this planet to be there.
Good, thank you. So that's very, so it's basically an evolution after the death of the star. And it is something that we are just starting learning now with this first observation. So I'm assuming you have a program now who's going to basically look at more white dwarf and search for more of those kind of objects, right?
Yeah, so now that we know that planets seem to be able to survive this process, it seems like they can survive the death of a star and then come back close into the star. We want to look for more of them. And in particular, we want to figure out, can this work for smaller planets as well, and especially rocky planets? So we have asked for observations with TESS of many more white dwarfs now. So we should be able to double the number of white dwarfs we've searched so far within the next year, and hopefully go even more in the years after that. And hopefully, once we do this, we can start to find more objects like this, more examples, and really understand just what happens to planets in all circumstances, not just this one particular case after their stars die.
Yeah, I would like to mention that this kind of system, it's easier to detect than a system with a small terrestrial planet, because basically, if to detect a transit, you need to have the planet aligned with the star in the same line of sight compared to us, right? With respect to us. In this case, because the planet is bigger, the likeliness of detecting an event like this, if there is a planet close, it's very high. Is that correct?
That's right. It's much easier to see the dips because they're much larger. In our case, a planet the size of Jupiter could block the entire light from the star, whereas around a star like our sun, it would block about 1% of the light. So the signal's 100 times larger. There are challenges, though, as well.
So how many? I saw a statistical brief analysis that there is, if you take the 100 stars nearby us, 8 of them are white dwarf. Mm-hmm. So that's give us a kind of an idea of the number of white dwarf in our universe. How many are you planning to survey in the future? Are we talking about 100, 20?
We expect to get several thousand in the next year with TESS. We've looked at about 2,000 already, and we found one planet. So in the next year, we hope to double that. And then in the next year, we may be able to double that again. So fingers crossed, we should be able to find more of these objects in the pretty near future.
Yeah, that's something I want to emphasize, is that this paper, which ended up being published in Nature, is the result of a survey of thousands stars. We always have the feeling, when you read a paper like this, we always have the feeling that, yeah, Andrew just took a telescope, observe a star, and boom, find a planet. It doesn't work like that. You observe thousands of them, probably, and then you didn't get lucky. You search for them, and you convince a TAC or an observatory committee to give you some time to observe those targets, to collect those observations. And that's one of the main difficulties in astronomy. We need to convince our colleagues to do those kind of observations sometimes. Good. We're
We got
having
a little bit
questions.
lucky with that though,
Yeah.
because as soon as we found the signal, we wanted to see whether it was real and whether it was really coming from the white dwarf and just how it appeared to be. And we were able to contact some amateur astronomers to take observations for us. So we have two collaborators who are amateur astronomers who have telescopes in their backyards in Arizona. And within about a week of us finding this object, we sent them an email and they were able to confirm that the transit was there. They told us exactly how much light was being blocked. And it was really helpful for us to convince these other professional telescopes that this was worth going after.
Yeah, that's very interesting that the technology are involved so much now that with a small telescope in the backyard, we can basically find or confirm the existence of an exoplanet. And in this case, an exoplanet around a white dwarf. I'm always amazed by this, by the potential of amateur astronomy, considering now the advancement of technology. And we should be very thankful for these people who dedicate their time freely. There's not
Absolutely.
amateur, most of them are more advanced than us in instrumentation to do those kind of observations. Okay, so we're gonna take some questions before I go to my last question. So Tony asked, how do we know that this is a gas planet and not a terrestrial planet?
We don't necessarily know the composition of this planet yet, but we think that based on its size, it really has to have at least some gas. We know of lots and lots of planets that are about the size of Jupiter, and without fail, they are all have gas. So this one we think must be that way as well.
Good. And Agatha is wondering if this spiraling that you mentioned, get the planet closer to the star, is still continuing, or is the planet in orbit, in stable orbit?
So it will slowly move inwards, but it's going to be in a stable orbit for a very long time. It will be, I think, billions and billions of years before anything happens. So it's actually survived the most dangerous parts of its journey right now and gets to live out the rest of its life in relative peace.
So I remind our viewers here that you can take more questions. Of course, I have one for you. So what's the future? You mentioned future work to search for more of those exoplanets around white dwarf. But what about specifically this one? What will you like to know and how you are going to do this?
Yeah, so we want to understand more about this particular planet. And one of the most important things that we can learn about a planet is how massive it is. So we hope to use the James Webb Space Telescope to learn this when it launches. So James Webb, like Spitzer, will also observe in the infrared, but it will be much more sensitive and much more powerful. So while Spitzer couldn't see any light from this planet, we think that James Webb might be able to. So if we can detect the light from this planet, we can find out just how massive it is, and therefore just how difficult it would be for it to get to where it is today. We also want to learn what's in its atmosphere, and we can do that with observations from telescopes on the ground or in space.
So let's go back to James Webb Space Telescope.
Yeah.
We just got the questions. As soon as you mention this name, the questions that come right away. So
Yeah.
when this thing's gonna be launched finally?
Could you say that again?
When are they going to launch the James Webb Space Telescope?
I think the launch date is for Halloween 2021.
Yes, that's correct. So let's be patient, okay? So this is the gigantic telescope that will basically open in space. It's been designed to conduct observations in the mid-infrared as well as in visible. So with this telescope, because it's large and in space, you have the sensitivity to see better. Basically, that's what you can see from the ground. So you mentioned the detection of the planet itself, because we may be able to detect the heat of the planet. In the paper, you mentioned something very interesting, that this planet may have a temperature, an equilibrium temperature of 165 Kelvin. I'm not going to ask you to convert this in Fahrenheit because I'm not able to do that. You can Google it. And that's maybe the coldest transiting exoplanet. So what's the interest? Why is this interesting?
Yeah, so it's very rare to find a planet that is lined up in this perfect transiting configuration that's so cold. And that's mostly because the white dwarf is so cold at this point. So there's a caveat here, which is that maybe this planet is a little bit more massive than we're assuming there, and it hasn't quite cooled off all the way to that. But that's something we can figure out later on. So if this planet really is that cold, it's very similar in temperature to Jupiter, but it poses a different question, which is what happens if you take Jupiter and you slow down its spin? Jupiter rotates every 8 hours or so. But this planet, we think, is tidally locked to its star, which means that it would rotate only about every 34 hours. So what can we learn about the physics of exoplanet atmospheres by taking Jupiter and essentially slowing down its spin and studying this star as a comparison?
Yeah, that's interesting that in astronomy, we can learn by observing those bizarre systems, basically, about our own solar system planets. I don't know what it's going to reveal, but maybe it's going to show that give us some information about the internal structure of Jupiter-like exoplanets like this one. Great, we have questions coming here. There is some easy ones. So one from Petteri. Is there any sign of life on this particular planet?
There is no sign of life on this particular planet. It's the size of Jupiter, so probably it doesn't have a surface for life to exist on. But we do think that this planet tells us something very interesting about habitability and the prospects for life. And the idea is we didn't know necessarily before this planet if things could survive the journey close into white dwarfs. And now we think we do. And now we think that Jupiter-sized planets can survive this journey and make it in without being ripped apart by the star's gravity. If a Jupiter can do it, then maybe an Earth-sized rocky planet can do it as well. And this is really interesting because white dwarfs have habitable zones too. Mm-hmm. You might not necessarily think that because they're dead stars, but they do still emit light. This is the leftover heat from their original star. So you have to be really close in to get enough light to be warm enough to have liquid water on your surface. But that's right about where this planet happens to orbit. So if a Jupiter can make it in this far, maybe an Earth can as well. And if that happens, it might even be in the habitable zone and might be able to sustain life long after the star it orbits died.
That would be extraordinary. What kind of life can you expect on a terrestrial planet which orbits around the star in half hour maybe, or maybe, I don't know, maybe 1 hour?
8 hours would be the right.
An hour?
8.
And receive light from a white dwarf. Like we're talking about life which is in the mid-infrared, right? Depend of the temperature of the white dwarf. It evolves, of course. But that must be a very different type of life, definitely.
Yeah, so this white dwarf is a little bit cooler than the sun. Its temperature is about 4,700 Kelvin. So okay. The light is a little bit redder than our sun, but not crazy, not as extreme as something like TRAPPIST-1. Mm-hmm. So you could potentially see similar light levels to slightly lower mass stars than the sun for billions of years, because by the time it gets to be that cold, it's not cooling off very fast. It's just not putting out enough energy to lose it.
Can you tell us how the white dwarf evolved into a dark dwarf? How long does it take to cool down? Is that we're talking about million or billion of years?
We're talking about billions and I think even trillions of years. So to cool down completely, it will be very, very long. The oldest white dwarfs that we know about still glow brighter than, or still are hotter than the lowest mass stars. So even the very oldest white dwarf, the first white dwarf to ever form, probably has a temperature between 3,000 and 4,000 Kelvin. So there's a long way to go before it goes from that to zero. And the colder it gets, the slower that happens. So it's a very, very long, drawn out process. So it's good for life because if you get close enough and you stay there, you'll have a good heat source for a long time.
Long period of time. That's an amazing thing, when think about that. Maybe there is civilization there for billions of years evolving around, surviving around this white dwarf. They were not there at the beginning, but basically those stars will live for quite a long period of time and provide enough source of energy for those planets. So, I
This
mean,
white dwarf has been a white dwarf for longer than our sun has existed.
wow, that is blowing my mind, basically. I didn't think about that today. Thank you for bringing this today in my mind. Wow. Okay. I think we are done. Anything else you would like to add about your research, your life, or tell us about what's going to be the next plan for you? You've been hired with University of Wisconsin-Madison like a year ago or something like this, right?
Yeah, so I just started there about a month ago. And I'm really enjoying my first semester of teaching, even though it's a little bit unusual to be teaching remotely. So I'm looking forward to that and to trying to learn more about the white dwarfs and their planets in our galaxy.
All right. And you're probably going to have a group and grow the group slowly. So if you are a student watching us right now and you want to work on exoplanets and exoplanet around white dwarf or things related to this research, they should contact you, of course.
Absolutely.
Thank you very much, Andrew. And I should mention that you have been with us in April to talk about Kepler discovery. So at this rate, we're going to see you again in a few months, right?
Sounds good.
We're always happy to see you. Thank you. Thank you to all our viewers. Don't forget to follow us on social media to know what's going on in the galaxy, to learn about life elsewhere on planet around white dwarf. Why not? Subscribe, press the button here, and follow us and visit our new website, by the way. Thank you very much, everybody, and have a good day, evening, morning, wherever you are on this planet. Bye-bye.